Yeah, thank you very much for organizing this. This was quite a challenge. Yeah, what I would like to present is research on the one side logic and on the other side images. This doesn't seem to go together quite so naturally, but I hope to convince you that it does. Okay, outline of the talk. I will go over some background that is not VSA, as Evgeny told us not to start there, but to explain the things that might not be so well known. And then I will come to the main portion of the context logic program. So I have probably quite a lot of logic in there, but that's the nature of the topic. Okay, this is the bigger picture, the activation bit vector machine, a variant of the VSA that is enabled for logics. So I have a reasoning layer here, perceptual layer here, and then also for imagery. So this is the intermediate between perception and reasoning. So background, I'm starting from the simple neuron-inspired bit vector format. Of course, this is VSA. And then as an addition, I'm also looking, or I've been looking into fuzzy logic as another source, and some other logics too. And then otherwise, I'm trying to be quite standard. So there is associative memory, specific perception circuitry. I'm not talking about that portion. So the implemented system comes from classifiers, classifier output upward, and from reasoning downward to perception or control application domain. I'm using is spatial reasoning in the widest possible sense. So here are some examples. I will discuss about mental maps that can come from language or experience, and show the TextMap Experiment. Then I have a level of language and time where we can do something like following route instructions. And then there is a level of reasoning, simple problem solving, which is again more complex. Example would be creating route instructions. So what do I want to talk about here is mainly here in this part. Explain how I can have a logical VSA reasoning system that outputs mental images or sounds or whatever. So I'll be talking about images, but this can be multimodal output. So a little bit on the logics background. Fuzzy logic, originally developed by Sade in 1960s, 70s. Goal was to bridge the gap between sensory input and computing. It was, or is, cognitively motivated. The idea is computing with words. And one of the key ideas is that adjectives in human language are more flexible and robust than numerical values which computers use. So here's an example. in natural language, we say, if the room is cold, then turn on the heater. If we describe this in terms of threshold values and how we should act when the measurement is between certain thresholds, things get a lot more complicated. So this becomes a complex program just to turn the heater on. So linguistically much easier. As a logical language, it is a generalization of many valued logics, the basic system is that of Lukasiewicz. Truth values come from the interval 0 to 1. This is good for some domains where we have control systems. And then a question one could ask is, could this be used to bridge the gap between sensory readings and higher level reasoning? Unfortunately, there are many negative results regarding reasoning engines for fuzzy logic. It turns out it has a high complexity, which means it has a high expressiveness as well. That means there must be some very complex things that we can represent with fuzzy logic. And this has been studied, and Hayek found out that any residuated lattice structure can be a semantics for fuzzy logic. So what does that mean? So any type of partial order with a meet operation and a join operation and complement. Okay. Now another family of logics, description logics, were targeting exactly at reducing expressiveness and complexity. So a whole hierarchy was built where one could select exactly the language one needed in order to represent whatever one needed. Description logics, the base language, where it's very fast, has class hierarchies, things like a car is a vehicle. But when we add sensory input, space or time, so-called concrete domains, description logics become get a high complexity. Now we're adding sensory values, and again we have a similar result as with fuzzy logic. It gets complicated. So is there something wrong with sensory values, space, time, and so on? Is this hard per se? And evolutionarily, we can say this must have been quite early, because it's important for survival to handle space, time, and sensor values well. We can also find in the literature specialized representational languages for space and time, which focus exactly on these abilities. So there are lots of calculi. I don't want to go into the details, but for a lot of relations like before, after, during meets, part of and connection, left, right, north, south, east, and so on. And many more relation systems have been studied, so of this important area. Now, several of those calculi turned out to be hard, but some turn out to be in a special class, the so-called Horn fragment. It's called Horn fragment because there is a mapping from statements in these simple formal languages to propositional Horn logic. And propositional Horn logic has linear satisfiability in reasoning. So now all this as introduction on the background. Now coming to the context logic program, the goal was to wrap up what we have here on and then develop a hierarchy like description logics, but that follows an evolutionary pathway. That is, the simple things should turn out to be fast, and more complex things should can take longer. So this is the hierarchy I came up with. We are starting with atomic context logic, atomic Horn context logic, and it says something like G1 and G2, or the intersection of G1 and G2 is part of D, and so on. This language is, and we can have a series of those simple statements, simple relational statements. And the satisfiability problem here is linear. So we are in propositional Horn logic, and we can actually simulate in this language all sorts of the propositional, the Horn fragment of several spatiotemporal calculi. But there is also a visual correspondence that I'll go into more detail later. Those correspond to point graphics, as I will show. So the next level here is CLA, so atomic context logic, and here we can have the sum of objects here, and then we end up in NP with satisfiability. So this is equivalent to propositional logic, but those are relational statements, right? So we have the intersection of G1 and G2 part of the sum of D1 and D2. Going up here in the hierarchy, we can not only, here we have the AND connection. If we allow not only AND, but also OR, negation, and so on. So here is a normal form. If I can say gamma 1 is part of delta 1 and gamma 2 is part of delta 2, then gamma 3 is part of delta 3. So I can I get a more interesting logic here, and in particular the expressiveness goes up. Of course, satisfiability becomes harder. This logic is equivalent to intuitionistic logic, and visually this corresponds to a series of images, so to a film. And then, this is with disjunctions. So, so CL0, gamma 1 is part of delta 1, and gamma 2 is part of delta 2. Then gamma 1 is part of delta, gamma 3 is part of delta 3, or gamma 4 is part of delta 4. So it gets more complex, and we have branches there. So that's what increases, probably increases the satisfiability problem complexity. And the full CL1, the first order logic equivalent, has quantification, so we can have general statements. So the lowest level down here can handle temporal before, after, during, north of, taxonomic, is, and logical relations between states. If we want to have something like overlap, we need CL0, partonymies, we need CL1. So we can do graphs actually just in this upper level. So general relational frameworks are quite difficult. So coming back to the architecture, where does this come in? We have the CL0, CL1 knowledge base up here. This goes down to the intermediate layer here, and can be visualized in this pathway, or we can come up from perception and have the two arms, so to speak, join here and be combined. So reasoning can be combined with perception here, and we get a mental image then. Okay. So the intuitive approach in problem solving, if we think about it, what we're doing, we read the problem and try to picture it, or we say we look at the problem from different angles. It seems a 2D visual or whatever, higher, lower dimensional, internal, sometimes also externalized vector representation, so 2D vector space representation of the problem seems to be helpful to solve problems. The visualization, having such a visualization feature could be useful for general intelligence. And we can also ask whether it can help with a symbol grounding problem. So we have a visualization here, so we can actually compare it to reality. Okay, now the experiment, the TextMap experiment, this is a simple application of this mechanism. Let me give you a little bit of introduction here. I say there are three ways in which we can read or hear a sentence. Purely syntactically, if you hear Schwerin is north of Berlin, it's quite late, maybe you just hear there are some words. Or associatively, maybe you think, okay, Berlin is a city, Schwerin maybe also a city, North Pole, and so on. Or we can hear it semantically, so we can say Schwerin is north of Berlin, and we imagine that for a second, it creates a mental map that has a resemblance to actual maps. So maybe you have a map of Berlin in your, of Germany somehow, a blob with Berlin somewhere in the east, and then Schwerin north of it, a little bit higher on that image. That takes a measurable delay when people do that. So there is some considerable cognitive effort to reach that semantic level. And the CLA reasoner has the side effect of being able to visualize. So now let's look into the details how this works. Let's imagine this image. A is north of B and B is north of C. So maybe you have A somewhere here, B somewhere there, and then C down here. C has a north coordinate, so to speak, of 1. B has a coordinate of 2, and A has a coordinate of 3. We can, in a very simple way, totally simplifying linguistics, we can say A is north of B, B is north of C, just using the implication here, separation. And if we have such a formula, logical formula, and CLA equivalent to propositional logic, that's why I can do this as brutally as I'm doing this here. If I have a logical formula, then I can describe the truth table, which is what I'm doing here. So now here it comes in in the columns. Those are very much like our VSA vectors. They are just well sorted and organized. But nevertheless, we have 50% zeros and ones for each of the columns here for representing our objects. And if we have a large number of them, we can be sure that each case is covered if we have VSA vectors here. So let's look at the truth table. And here you can see what the implication here does. It adds a 0 where A is smaller than B. Those are exactly those two cases. Here, that's where we have a 0. And C here likewise. And as I add up those zeros, so I subtract them from 1, and then I get my formula phi here. Now, let's look at the formula A and N. And what I can do is I can focus on a certain part of phi by looking at what portions of A and N actually highlights or what it masks, those portions here. And you can see those 3 here are you can't see that here, so let's stay here. So those 4 ones down here, 1 0 1 1, so 3 ones I have. Those are the only portion that can be seen if I filter A and use A and N as a filter for phi. And if I now sum those values up, I get a value of 3. So A and N and phi is 3. I can do the same with B and N here. So B and N highlights those 2 portions of phi, and you can see those are 0 here and 1 there. So I get a sum for B and N and phi. That is 2. If I do the same with C and N, I get a sum that is 1. So for I literally can see that the north coordinate of A in phi is 3, and for B is 2, and for C is 1. Now I can have the a reasoning imagery algorithm on the VSA for that. I'm running out of time, so I'll be skipping a little bit over this, but the only thing to do is, coming from natural language, quite straightforward. I take out the delta part and the gamma part, and then I have the corresponding formula. We just need pairs of negative and positive variables, and that's the whole representation in on the symbolic level. And then I go down and I can calculate the representation of one sentence here. So this is the sentence, and I can calculate the representation by using bitwise and bitwise negation. to have a negative representation of one sentence. And I can calculate the positive representation of a set of sentences. Then I start with the vector that has all ones, and I those representations of each of the sentences. When I have this representation of a whole set of sentences, I can ask queries like satisfiability is simply whether the sum of all the entries in my long bit vector is 0. And I can ask for the north coordinate of A by asking sigma and the sum of all the ones in sigma and the representation of A and the representation of north. So how good can this be? We can ask, is this just a random property? No, it's systematic because the logical implication works exactly that way. It removes the positions where x is larger than y. And I can have more than one relation in this manner that I demonstrated because the relations act as contextual parameters so that I can separate the different relations from each other. Now the second question, does this scale? What I'm doing here by summing up the ones, I'm doing model counting, and this is usually considered intractable. Also, I've been using truth tables in my examples, so this does not scale. But with a VSA implementation, this behaves very similar to human working memory. I get a linear complexity reasoning mechanism that way. It's probabilistic with graceful degradation properties. So how good is the output? And I was donated this beautiful long example. I don't know whether you can picture that in your mind, but some human being could. And south is quite easy. You just need to switch around the parameters. But so for a human being, this is already quite difficult. But I can feed that into the system, and we get this kind of quite nice map out of it. So you can see the east coordinate for Pittsfield puts it on the top of all the cities, and yeah, the east coordinate is quite far in the east, and so on. So it's quite good, and you see where it has errors. The original has errors and typical alignment problems here. This is not right in reality. They are also in the names of the cities. Okay. In conclusion, the context logic hierarchy, a hierarchy of logical languages developed to mirror the evolutionary development of cognition. So what's simple in cognition should be simple there. And a reasoner can be implemented based on the VSA and has many interesting properties. Complexity is not worse than other approaches. Visualization, the visualization property is costly with the truth table mechanism, then it's exponential and does not scale, but probabilistic with the linear implementation with the VSA. we have an indicator that this is quite relevant for the grounding problem. If you see the match between reality in the map and what my experiment participant had in his mind was quite grounded in reality. We can say, yeah, this is right, or this does match reality or not. It gives us some interesting insights into how language could have evolved, because it provides something that is useful even before we have more higher cognition. And yeah, there are a wealth of possible applications in small scale human-like AI, such as ethical robots, which can picture the consequences, and actually this can be routed to their perceptual input. Yeah, thank you. I'm sorry for going over the time.
I think you're right on track. So thank you, Hedda. Any questions to Hedda? Please unmute yourself. In the case of questions.
I have one.
Yes, please.
Hedda, with the truth tables you had earlier, what does each row correspond to in the truth table?
It's just a combination, a specific combination. So in the VSA, if I have 10,000 bits, then I have probably every case covered, as long as I don't have too many variables.
So do you have, does each row in the table then also correspond to a single bit in the BSA? Is that right?
So these actually, this doesn't work. Okay. So the columns are the VSA vectors simplified, yeah. And then it's probabilistic, because I can't ensure that each case is actually going to be in the in my combination of values. But if I have 10,000, it's quite probabilistically quite likely.
Okay,
as long as I don't have too many variables.
So if you have a literal value like A, then effectively that's a column vector, and it's just a VSA of randomly chosen bits in the usual fashion.
Yeah.
Okay, sorry, I was just trying to understand the mapping across the VSA. Yeah, thank you.
It's hard to present 10,000
sure.
bit columns.
Yeah. Here I have a question, if you permit. In your system, so when you construct this truth table, is it possible to query it with, for example, with such question as, give me all cities west of something? I mean, how this would be implemented? Or maybe
I would think that so we have this mechanism which can create a visual representation, and then you can just inspect this visual representation, so it gets fed into the perception again. So yeah. So I don't.
Well, I need more time to understand this concept, but definitely this is very important. I mean, this logical reasoning, it's not trivial to implement at all. I have another question, but maybe, I mean, well, as I understand,
let me bring up the the architecture, because so in the architecture you have, can you see it? Yeah.
Yes.
So in the architecture here, I have the mental image down here, and I didn't draw an arrow here, but that's the basic idea, that you can inspect the mental image that you construct in that way, and then and that's where you would find your cities.
But then following this logic track, maybe it's not directly applicable to your current state of, I mean, to your solution in the current state, but did you think about implementing the resolution algorithm, any resolution algorithm, like, I mean, typical for propositional logic or something?
Yeah, no, so this is the algorithm, and yeah, what's actually quite nice is that it is linear. So that's a lot, yeah, actually simpler than, and you can imagine how this could actually biologically happen, because those are just primitive operations with which we combine the vector representations. I looked into different variants, and I have it in my overview slide. I say something that the original or one of the original proposals was assigned a sort of tableau prover. So formally, this is you can interpret it as a kind of tableau prover as well. And I have I'm using basically the tableau approach for the higher logics of CL0, CL1. So this is CLA, the atomic fragment here, just in that hierarchy.
All right, so I see time is now 5 or 6 past 11 p.m. here in Sweden. Anyways, lucky you in Melbourne and the US. We still have some time to go. So I guess, as promised, we will keep the schedule. So we will end the seminar or webinar by now. And maybe I can, Hedda, if you can share your screen, I will show one a snapshot of my screen very quickly. Yes. And with this snapshot, I just want to remind you about upcoming webinar, which will happen in 2 weeks' time, so 1st of June, same time, 8 p.m. GMT. Once again, calculate your own time offset yourselves. And there we have 2 scheduled talks by Dennis Clayco and Stefan Reimann. So you're warmly welcome to attend this seminar, and I thank you for your attendance today. So thank you and goodbye. So I stop recording.
Thank you very much for organizing.
Thank you for attending.
Thank you.
Thank